Okay, so today we are talking about oxidation reduction, and I've prepared a note-taking guide on it. So we call it redox for short, but it's called oxidation reduction. That's a long thing to write out, so that's why we just call it redox for short. Redox reaction involves the gain and loss of electrons, which again, reminder, we represent as E minus, right? And we assign oxidation numbers to atoms to show this gain and loss of electrons. And now this is a very important rule. So put a star next to this. Very important. The sum of the oxidation numbers, oh, I should say the sum of the, not the sum of the oxidation numbers, the sum of the contributions of the oxidation numbers. Okay, the sum of the contributions of the oxidation numbers must add up to the overall charge. So it's either going to be 0 if it's a neutral compound, or it'll be plus or minus some number in ions. Okay, the sum of the contributions must add up to the overall charge. Now I say contributions because the oxidation numbers themselves are not going to add up to the charge, but the sum of the contributions will add up to the overall charge. That's a really important detail to make sure you correct in your note guide. So you've got to memorize some rules. Sorry. That's just part of it. You need to memorize some rules, but the good news is they're really easy rules. These rules are not difficult at all. So if you can just spend a few minutes committing these things to memory, you're going to be fine. So these are your always rules. If you have the choice between following an always rule and following a usually rule, follow your always rule first, and then if you have to, follow a usually rule. But again, this must be learned. Okay, memorize it. Memorize implies that you're gonna remember it short term and then forget. So that's why I prefer to say learn, but I'm a realist. I know that you're probably just gonna memorize it. So, right, learn it, please learn it. Okay, a pure element in its most stable form has an oxidation number of 0. So for instance, if we've got iron and it's solid, right? Oxidation number would be 0. Iron metal, copper metal, zinc metal, silver metal, whatever, right? Or if we had chlorine gas, bromine gas, hydrogen gas, right? That would also have an oxidation number of 0. So a pure element in its most stable form would be 0. Monatomic ion is its charge. So for example, Fe2 plus oxidation number is +2. For N3 minus oxidation number is -3. Okay, so if it's a monatomic ion, monatomic, right? Keyword there being monatomic. The oxidation number is just its charge. All right, your group 1 elements. So who remembers where group 1 is on the periodic table? It's these guys, right? Hydrogen, lithium, sodium, potassium, etc. These guys, oxidation numbers are all +1. Okay, so the oxidation number of lithium in a compound would be +1. Group 2 elements, so that would be beryllium, magnesium, calcium, etc. These guys' oxidation number is all +2. Okay, you can always count on that rule. Oxygen in a compound, not oxygen gas. Okay, oxygen gas would be 0, but oxygen in a compound is always -2, except in peroxides. So the only peroxide really you've probably ever seen is H2O2, hydrogen peroxide. Right? Its oxidation number there would be -1. So 99 times out of 100, it's going to be -2. So just ask yourself, is this a peroxide? The answer is no. You can say, follow this always rule, it's -2. This is the rare exception. Okay, so these are our always rules. These are the rules that we can always follow. No exceptions other than this one tiny little one right here. Our usually rules. So usually, group 3A, so that's the boron, aluminum, etc. group. These guys are usually +3. Not always, but usually. Group 5, that's the nitrogen, phosphorus, arsenic, etc. Those guys are usually +5, but not always. And group 7, that's fluorine, chlorine, bromine, iodine, etc. Those guys are usually -1, but not always. Okay? So again, when we do these kinds of problems, you're going to have to rely on having these rules memorized. And if you have to choose between, do I follow an always rule or do I follow a usually rule, which one do I follow first? Follow your always rule first, and then if you have to go back and follow a usually rule, do that second. Okay, but always follow these rules first, these guys second. Is everybody good on our usually and always rules? Yes, ready to do some examples? This is not really that difficult. It just requires you to memorize this part. Once you've got this part memorized, the rest is really easy. All right, I got lazy with my formatting here, so let me fix this real quick. Subscript, subscript, superscript, subscript. Okay, let's zoom in on that. I forget that my camera doesn't pick up really well if I don't zoom in really far. All right, so let's do some examples. We can probably fit all of these on the same screen. Okay, so when you're getting started, what I recommend is making yourself a little chart, okay? You'll feel a little goofy doing it, but it'll help you here at the beginning. And then once you're good at it, you can just do this in your head. So make yourself a little chart. This is your oxidation number, and this row is your contribution. Okay, so first, KMnO4. Does that compound have a charge? Is there any sort of charge? Is it KMnO4 plus or minus something? Or is this molecule neutral? This compound does it have charge? No, so all of these contributions need to add up to 0, right? Because this is neutral. There's no charge. All right, so all of our contributions need to add up to 0, okay? So now let's follow the rules that we know. Potassium's in group 1. We have an always rule for group 1. What is that? Group 1 elements are always +1. So its oxidation number is +1. There's 1 potassium here, so its contribution is also +1. Does that make sense? Okay, we don't have any rules for manganese. Manganese is in the D block. We don't have any rules for transition metals, so we'll have to figure this one out. Oxygen, is this a peroxide? No. So oxygen in a compound is always -2. But there are 4 of them, so what's the contribution? -8, right. Okay, so for this to add up to 0, what must the contribution of manganese be in order so that 1 and -8 gives me 0? The contribution here needs to be what? +7, right. Does everyone see why this contribution needs to be +7? Because we want this bottom row to add up to 0. Now there's only 1 manganese, so that means that its oxidation number is the same as its contribution. So this row, these are my answers. Okay, this row down here, this is just helping me keep my records. Okay, so the oxidation number of potassium is +1. Oxidation number of manganese is +7. Oxidation number of oxygen is -2. This bottom row here is just to help me stay organized. Does everyone see how we did this? Does this one make sense? Are you okay if I erase it? I'm recording this, so it'll be up later if you need to go watch it again. Okay, let's do this one. Chlorate. Cl O3. And now, this is a polyatomic ion, right? Because look, it's got a charge. So my contribution row, what do my contributions all need to add up to? This has a charge now, right? So what do my contribution row need to add up to? -1. Okay, does everyone see why it adds up to -1? Because this is a polyatomic ion. Okay, we have a usually rule for chlorine, but we have an always rule for oxygen. So who do we follow first, the usually or the always? We follow the always rule first. This is not a peroxide, right? So what is the oxidation number of oxygen here in this compound? Oxygen in a compound is always -2, and there are 3 of them, so the contribution is -6. Okay, what must the contribution of chlorine be so that this row adds up to -1? +5, right? So +5. So these are my answers. Notice chlorine is not following its usually rule. That's why it's called a usually rule and not an always rule. Chlorine's definitely not following that usually rule here. Is everybody good on how we did this one? Any questions on chlorate? Okay, let's do calcium hydroxide. Now for your chart, if you want to go ahead and distribute that too and write it like this, that's fine, but just know that that's not a correct formula, right? If you write CaO2H2 on a test, I'll mark it wrong. But just for your chart, so you don't have to deal with that parentheses, you can go ahead and distribute that. Okay. Does this compound have a charge? No, it's neutral. So this all needs to add up to 0. Okay, we actually have always rules for all of these. So we don't even have to do any figuring out. Calcium's in group 2. Group 2 elements are always +2, so the contribution is +2 because there's only 1. Oxygen is always what? -2, and there are 2 of them, so that gives me -4. Hydrogen's in group 1. Group 1 elements are always +1, and there are 2 of them, so that gives me +2. Does this add up to 0? Yes. So here, these are all always rules that we're following, but we do the bookkeeping row just to make sure that we're staying on track. Okay? That's kind of like a self-check here. So again, once you're good at this, you can just do it in your head. You can look at it and go, well, +1, -3, whatever, right? But when you're in the initial stages of just learning how to do this, I do recommend making a little chart because it'll help you stay organized. And a lot of students are very visual, and seeing something visual for most students is very beneficial. Any questions on these 3 examples? Okay, so I've got a few for you to try. I'll pause the recording. Take a minute and try these 9. Copper 2, magnesium chloride, copper 2 nitrate, copper metal, iron 3 sulfate, chlorine gas, ammonium ion, carbon dioxide, and carbonate ion. So take a minute, try these problems. Let's go over these. All right, copper 2 ion, that's just Cu2 plus. So what's the oxidation number of a monatomic ion? +2, right. Any questions on number 1? It's really, really easy, right? All right, magnesium chloride. What's the formula for magnesium chloride? It's MgCl2. All right, so if we make our little chart, we got an always rule and a usually rule. So we've got our oxidation number and our contribution. This is going to add up to 0, right, because this is neutral. We have an always rule for magnesium. What is group 1? Always. I mean, group 2, always. Plus 2, so it contributes plus 2 as well. We have a usually rule here, but we could just figure it out. For this to add up to 0, what must the contribution be? -2, and there are 2 of them, so each one of these is -1. So it does follow that usually rule. So magnesium is plus 2, and chlorine and chloride is -1. Do we agree? All right, let's do copper 2 nitrate, which would be CuNO3 what? Do you need a number outside the parentheses here? 2. 2, that's right. All right, so let's make our chart. And again, if you want to go ahead and distribute this for your chart, that's fine. CuN2 and then O6. Cursor's like right in my face. It's kind of driving me crazy. There we go. Okay, for our chart, this is a neutral compound, right? There's no charge. So this adds up to 0. That's our contribution row, our oxidation number row. Do we have any rules for the transition metals at all? No rules. You'll have to figure out what copper is. We have a usually rule for nitrogen, and we have an always rule for oxygen. So let's follow our always rule first. What is oxygen here? -2. So it contributes, there are 6 of them, so its contribution is what? -12. Okay, now we have no choice. We have to follow that usually rule, right? Because our options are nothing, no rule, and usually rule. So obviously we follow our usually rule. What is nitrogen? It's in group 5. What are group 5 compounds usually? Plus 5. And there are 2 of them, so this contributes
10.
Plus 10. So what must the contribution of copper be? Plus 2. And since there's only 1, its contribution is the same as its oxidation number. So copper is plus 2, nitrogen is plus 5, and oxygen is -2. Do we agree on number 3? Okay, copper metal, that would just be Cu solid. So its oxidation number would be what? 0. Right, that's a pure element in its most stable form. So that one's easy. Iron 3 sulfate. What's the formula here? Fe, then what? SO4, 3. Okay, so let's go ahead and distribute that 3 for our chart. We've got Fe2, and then distribute that 3. So S3, and then 3 times 4 is 12. This is a neutral compound. Right? Oxidation number, contribution. This adds up to 0 because this is a neutral compound. Oh, I should have helped you out here because sulfur's in group 6. You don't have any rules for group 6. Correct. All right, so you probably couldn't do this one because I didn't tell you about sulfur being in group 6. All right, so I wouldn't give you one like this on a test because I didn't give you any rules about sulfur, and I forgot about that. All right, so on a test, I would not give you a sulfate, but let's see. Its oxidation number here would be -6, I believe. Let's prove it to ourselves. Let's see, so we've got -2 here, so that's -24. And iron does end up being +3, so that is +6. So then what does this contribution here need to be? 18 plus 18. So yes, that does end up being +6. So yes, this would not be on a test. Sulfur and sulfate is +6, but I forgot that you wouldn't know that off the top of your head. My mistake there. Okay, chlorine gas has the formula what? Is chlorine gas monatomic or diatomic? It's diatomic, right? So that's just CO2. Is that a pure element in its most stable form? Yes, so its oxidation number is 0. All right, let's do ammonium ion. What's the formula for the ammonium ion? NH4 plus. So the contributions need to add up to what? +1, right? Adds up to +1. This is our contribution. This is our oxidation number. So we have a usually rule, but let's follow the always rule first. Hydrogens in group 1, those guys are always +1. So contribution makes it +4. So what must nitrogen be in order for this to add up to +1? -3. So nitrogen's -3 and hydrogen's +1. Questions on NH4 plus. What's the formula for carbon dioxide? That's CO2. All right, let's make our chart here. That's neutral, right? There's no charge. So CO2. Oxidation number, contribution. This adds up to 0. We don't have any rules for carbon, none. We do have a rule for oxygen. It's always what? -2. So this is -4. So what must carbon be? +4. So +4 and -2. And then the last one, what's the carbonate ion? What's the formula there? CO3, 2 minus, right? So CO3, 2 minus. So this contribution needs to add up to what now? -2, right? Because that has a charge. Oxygen is still -2, and there are 3 of them. 3 times 2 gives me -6. So what must carbon be? It's still +4, right? So same in both of these compounds. How do we feel about doing this? Again, sorry about throwing the sulfate on there. I forgot about the fact that you wouldn't know that one. Any questions on how to do this? Feeling pretty good? So now that you know how to do it, the only thing left is just identify redox. Is it redox or is it not? So if I give you a reaction and I ask you, is this a redox reaction? You would just need to apply this procedure to it and answer the question. So oxidation versus reduction. There are 2 ways to remember it. You pick the one that works for you, and I know my colleague next door uses this method. Well, he uses one of these methods. This is the one that I learned. Leo says grr. So if you think like, you know, if you think about your constellations, right? Isn't there a constellation Leo, the lion? All right, I learned this when I was 15, okay? So bear with me. Right there's Leo. He's a lion, and he says grr. Okay, so what does that stand for? Leo, lose electrons equals oxidation. Gain electrons equals reduction. Okay, Leo says grr. Lose electrons equals oxidation. Gain electrons equals reduction. This is the one you'll see me using a lot because, like I said, I learned it when I was 15, so it's kind of been in my brain for a long time. And then there's another method. My husband actually taught me this method when we were in graduate school because we both were teaching Gen Chem, and he said, hey, have you ever heard of oil rig? I said, no, I haven't. And I know this one gets taught next door as well. Oil. Oxidation is loss of electrons, right? Reduction is gain, again, of electrons. Now, the thing you need to keep in mind, and I don't care which method you use, so either one works, okay? Electrons are negative, right? They have negative. So if you gain electrons, that means that your oxidation number, is it going to go up or go down? Electrons are negative, so if you gain something that is negative, is it going to make your oxidation number go up or go down? It's going to go down. Okay? If you gain electrons, your oxidation number goes down. Think about this. Your test is on Wednesday, right? If I said, you know what? You're going to take your test right now. Put everything away. You'd be kind of mad, right? Your attitude would be negative. I just put something that is negative on you, and it brought down your attitude, right? Likewise, if you lose electrons, what happens to your oxidation number? It's going to go up. So your test is on Wednesday. If I said, you know what, guys? I know you guys know this. You don't need to take the test at all, right? You'd be thrilled. You'd be happy, unless you just want to take a test. You'd be jumping up and down and doing backflips, right? I removed something that is negative, and now you're like, woohoo, right? So just remember, if you're gaining electrons, your oxidation number is going to go down. It brings you down. Whereas if you lose electrons, you're getting rid of something that is negative, your oxidation number is going to go up. So I don't really care which way you remember it. If you want to think of your own mnemonic device, great. But these are the two that I am familiar with. And like I said, you'll be hearing me say Leo and Ger, because that's the way I learned it long, long, long time ago, and I just stuck with it. So high school chemistry teacher, if you're watching this video, here's a shout out to you. All right. Here's an example. Boy, I don't like the fact that I have to zoom in out so much. I'll zoom in a little bit more. Iron metal reacts with copper 2 chloride to produce copper metal and iron 3 chloride. And technically, I wouldn't even need to tell you what the products of that reaction are, because could you do this? This is just a single displacement reaction. You could do this. I don't need to tell you the products, but I just happen to here. So let's decide, is this redox or not redox? So iron metal, that's just plain old Fe, right? Reacts with copper 2 chloride. So that would be CuCl2. That would be aqueous. It's a solution. You're going to produce copper metal, so that would be Cu, solid, and iron 3 chloride, so that would be FeCl3. All right, this isn't balanced, right? So we need to balance it. So you need a 3 here, and a 2 here, and a 3 here, and a 2 here. So my question to you is this redox? Well, for something to be redox, you have to have both an oxidation and a reduction. If there's no change in oxidation numbers, then it cannot be redox. If there is change in oxidation numbers and one gains electrons, the other reduces, the other one accepts electrons, then there is a redox. So let's go through and assign our oxidation numbers. This is a pure element, its most stable form, so its oxidation number is 0. All right, let's do CuCl2 real quick. We'll just make ourselves a little chart. This is neutral, so it's going to add up to 0. All right, this is my oxidation number. This is my contribution. I don't have any rules for transition metals, so I have to follow my usually rule. Chlorine is in group 7. Group 7 elements are usually what? -1, so -2, so therefore +2. So +2 -1. All right, this is another pure element in its most stable form, so that's 0. And then FeCl3, so we've got FeCl3. Again, no rules for transition metals, but we have a usually rule for group 7. Group 7 elements are usually -1, and there are 3 of them, so -3. So therefore, iron must be +3, right? So +3 and -1. So the first thing you do is you've got to go through and give everybody oxidation numbers. Now, if you want to clean things up, you can ignore the ones that are not changing. There's one element here whose oxidation number doesn't change. What is it? Chlorine, so you can just ignore it. Right? Chlorine is not participating, it's a spectator. Because if you wrote a net ionic equation, it would come out as a spectator. So you've got iron going from 0 to +3. Did that lose electrons or gain electrons? I've heard both answers. Which one is it? Your number went up. You lost something that is negative, so that means your oxidation went up. So you have lost electrons. So that would be oxidation, right? And copper went from +2 to 0. Did that lose electrons or gain electrons? That gained electrons. So what is that? That's reduction. So to answer the question, is this redox? Yes. Yes, it's redox. All right. Iron is oxidized. And copper is reduced. Do we agree? Also, we have one other piece of data to add to this. It's a little vocab word. Oxidizing agent and reducing agent. Okay, the word agent means allows to occur. So if I'm the oxidizing agent, that means that I myself am getting reduced, but I'm letting you get oxidized. Okay, if you are the agent of that, that means you allow that to occur. So iron is oxidized, and that makes it reducing agent. Does that make sense? If you get oxidized, you're allowing someone else to get reduced. Okay? Copper is reduced and is the oxidizing agent. Because if you get reduced, you're letting someone else get oxidized. Okay? So these two are always going to be the opposite of each other. Whatever that gets oxidized is the reducing agent. Because remember, agent means allows to occur. So if iron gets oxidized, it's allowing something else to get reduced. And if copper gets reduced, it's allowing something else to get oxidized. Does this make sense? Do we see how to do this? You have to have both oxidation and reduction. If you do this process and you somehow come up with 2 oxidations, something's wrong. You need to go back and check your numbers, okay? Because you can't have one without the other. It doesn't work that way. Is everybody good? I guess I should ask that before I erase. Is everybody good on this problem? Yeah. All right. We've got one more to do, and then I've got some problems for you to do on your own that we will go over. It says you try. Let's just do them together since you're going to be doing some on your own here in a minute. Let's just do these together. All right. Magnesium metal reacts with hydrochloric acid to produce hydrogen gas and magnesium chloride. Is this redox? Magnesium metal reacts with hydrochloric acid. What's the formula there? HCl to produce hydrogen gas and magnesium chloride. We want to know, is this redox? First, we need to balance this. You just need a tube right here. Okay, pure element in its most stable form. So 0. Hydrogen's in group 1. So it is +1. That means chlorine must be -1. Pure element is most stable form, so this is 0. Magnesium's in group 2. These guys are +2. Chlorine here must be -1. Again, we have a spectator. And if you write a net ionic equation, this would come out as a spectator too. Chlorine is a spectator. Does the fact that there's a 2 in front of this have any effect on the oxidation numbers? No, that 2 is just telling you how many you have, okay? So you can look at this pretty quickly and tell that it's redox because you've got 2 things that are 0, right? So therefore, someone's got to go up and someone's got to go down. Magnesium goes from 0 to +2. So is that the oxidation or the reduction? Is it losing electrons or gaining them? Right, that's the Leo. And hydrogen's going from +1 to 0. So is that losing or gaining? That's gaining, so that's the reduction. So is this redox? Yes. Magnesium is oxidized and is, what is the agent here? Is it the, if magnesium is oxidized, what agent is it? It would be the reducing agent. And hydrogen is reduced and is the oxidizing agent. So yes, this is redox. Remember, you have to have both oxidation and reduction. If you have 2 reductions somehow, your math is incorrect in your oxidation numbers. You need to go back and double check. Because you have to have both. You can't have one without the other. Somebody's got to lose electrons, and somebody's got to accept them. How do we feel about this one? Good, good, good. All right, we're going to do this last one, and then I'm going to turn you loose on some problems. Calcium chloride reacts with sodium hydroxide. I wouldn't have to tell you the products of this reaction because you could figure this out on your own. This is just double displacement. Calcium chloride is CaCl2. That would be a solution. Reacts with sodium hydroxide. So that would be a solution. You're producing calcium hydroxide. So that would be a precipitate. And sodium chloride should be aqueous. And I want to know, is this redox? So let's go through and assign all our oxidation numbers. Calcium's in group 2, so that's +2. Chlorine here would be -1. Do we agree that this is -1? If this is +2, this is -1 to contribute -2. Sodium's in group 1, so it's +1. Oxygen's always -2 in a compound, and then this is +1. We've already done this one. Calcium's +2, oxygen's -2, hydrogen's +1. Again, this 2 just tells me how many I have. +1, -1. Okay. Let's cross out the ones that do not change. Calcium starts as +2 and ends as +2. Chlorine starts as -1 and ends as -1. Sodium starts as +1 and ends as +1. Oxygen starts as -2 and ends as -2. Hydrogen starts as +1 and ends as +1. So is this redox? No, this would not be redox. And why? Because no change in oxidation numbers. Okay, this is a precipitation reaction. You're forming a precipitate, so if you mix these 2 solutions together, you would see a white precipitate and go, woohoo, I made a precipitate, but it would not be a redox reaction. Okay, so not all reactions are redox, and here's an example of a double displacement reaction that forms a precipitate, and you go, wow, that's great, but it's not redox. It doesn't change oxidation numbers. You can't have redox if there are no changes in oxidation numbers. How do we feel about this? All right, I'm going to stop the recording here, give you some problems to try.